Hi, Zaid. I would like to thank you again for coming to Stats 385 Theories of Deep Learning. Can you tell us a bit about yourself and your academic journey?
Yeah, sure. So I grew up in France. I did my undergrad in classe préparatoire, which is a typical French system where you take a lot of mathematics and physics courses. And then I went to École des Mines, and then I did my PhD in Telecom Paris Tech on kernel-based methods for hypothesis testing. I spent a few months in Carnegie Mellon, and then I quickly got a permanent position in INRIA, which is a research institute in applied mathematics and computer science. I spent 5 years there in a team doing machine learning and computer vision. And then I spent 1 year in the Courant Institute in New York University in Yann LeCun's group. And I joined University of Washington last fall.
Great. So since this course is about theories of deep learning, I would like to ask you, what do you think are the main theoretical questions in deep learning that can be answered by theoreticians? If you can give us 3, that would be great.
Okay, sure. So I think one important question is the question of invariance and how it relates to data. In the sense, how can we learn from data invariances from the, say, visual objects or sounds? So invariances are very well described by, group actions in math. And but what do we mean exactly by approximate invariance? This is still unclear. So we know what it means to be exactly invariant, like perfectly invariant. We know also what it means not to be invariant, right? Because this usually leads to disappointing performance for machine learning methods when they apply to perform visual object recognition, for instance. But what is in between? So every time we try to describe this, there are there's very little progress on how can we describe in quantitative terms, like give a precise mathematical definition. What is approximately invariant, being approximately invariant, to what extent? How do we measure how invariant the system is? So those questions, and how do we learn this from a sample of data? Those questions, I think, are important challenges for deep learning modeling.
Is there any other theoretical questions that comes to your mind other than invariance?
Yeah, so there are 2 other questions. So one that is actually quite related to my recent research is how do we train deep learning models? So when we frame the training of deep neural networks, it usually leads to non-convex optimization. So in machine learning community, there's been a lot of work in convex optimization, large-scale convex optimization over the recent years. And now we're talking about non-convex optimization. So one thing that strikes me is, as a mathematician, so every time we refer to an object as non-this, whereas this is well-defined, usually means we're lacking theoretical tools to describe what we're talking about. So non-convex optimization is just a huge, it's basically everything that is not convex, right? So that's it includes all possible functions, weird functions in the world. We still have to define particular classes of functions that are non-convex, and for which we can derive guarantees in terms of how much time will it take to optimize these functions to get close to a global minimum. And so there's been a few advances in this direction. So recently, we've narrowed down the class of functions. Those are called weakly convex functions, for which we can analyze gradient-based algorithms and accelerated gradient-based algorithms and characterize their convergence. But there's still lots of work to do to come up with a function class that actually describes the functions that are optimized when we train deep neural networks.
So that was the second.
That's the second, yes.
Third.
So finally, so I think the mainstream approach to train deep neural networks is to assume that we have labeled data. There is, say, images along with their label category, and then apply an algorithm that's called stochastic backpropagation of gradient, which is somewhat principled but also somewhat heuristic. and it's a supervised learning algorithm. So we always assume that somehow we came up with this huge labeled data set. In most cases, we collect this data set through by scraping the web, and then having individuals actually annotate the data manually through crowdsourcing. And in science applications, this is often not realistic, but sometimes it's not even possible, right? So we need to know if we can learn feature representations using unsupervised learning. And it seems that a lot of what deep neural nets are doing could be achieved by unsupervised learning method. So if we look at the process of learning feature representation performed by deep neural networks, it seems that at least a significant fraction of it could be done by using unsupervised learning techniques instead of using supervised learning and stochastic backpropagation of gradients. So that's the third.
Okay, great. So now comes to some non-technical questions. So if you were to pick one alive mathematician to work with on the theory of deep learning, who would that person be?
That's an interesting question. So actually, I don't think this should be an isolated endeavor. I think to tackle building the challenge of building a theory of deep learning, I think we need a variety of points of views.
But it's personal. Like for you, who would be one mathematician that you would pick to collaborate with on the theory of deep learning?
But I understand your question, but I wouldn't be happy just with one mathematician, right? So I would like to pull inspiration from several subfields of mathematics. So I think there would be approximation theory, for instance. There would be
Can you give me 3 names? I'll give you a leeway on the names.
So definitely, on the approximation point of view, I mean, Stéphane Mallat came up with this beautiful theory called scattering transforms that relates to deep neural nets. So that's definitely.
Stéphane Mallat is one. Who would be the second?
So for the optimization part, it would be Arkady Nemirovsky. And I need a third one. And there's a probability part, I think, to describe the landscape of local minima. That would be Gérard Benarous.
Okay. And so, as my last question, I would like to give you a topic, and you give me up to 3 words. It could be 1, 2, or 3 about them. MusicNet.
Yes.
Just yes.
Sorry, so, I missed the question.
So
up to 3 words.
Up to 3 words about the topic I give you. You can give me up to 3 words.
Oh, large label music data set. So that's 4. Okay.
Stéphane Mallat.
Yeah, scattering transform.
Scattering transform. Dropout.
Yeah, no comment.
RKHS.
Positive definite.
Stanford University.
The top.
Thank you. So I'm going to pass it.
Well, Zaid, thank you so much for traveling from UW to Stanford to share all your insights with our class Theories of Deep Learning. You're the only theoretician that I know who's actually competed meaningfully in the ImageNet competition. Could you share with us your insights about, 1, whether it's a good thing for theoreticians to compete in that way, and 2, whether competitions as a whole are a beneficial phenomenon?
So I definitely think participating in those competitions and evaluating the methods on public benchmarks. I mean, I think competitions are, say, a sensationalist way of doing public benchmarks every year with lots of means. But so I think this is it's a healthy way I think on a yearly basis, participating to these competitions is actually a healthy habit, because it allows to see how relevant some theoretical progress are for real-world applications. On the other hand, sometimes the results of these competitions can be, at least from a scientific point of view, can be disappointing, because one can just paste together many methods and then win in those competitions. And I think if looking at the top, at the winners of the Kaggle competition is actually very interesting. Often we see it's just ensemble methods, lots of methods integrated together, and you win by a small percentage. I'm not sure how interpretable those models are. How is there an underlying, what's the main idea? What is that led to this good performance behind those numbers? This is very unclear. So in this sense, if the results, the winning entries in those competitions look like this, it's not helping much, I would say. So I think participating to these competitions by keeping the method as principled as possible and limiting the number of hacks or things that are too data driven, I think it's still helpful and informative.
So you competed more specifically in the famous 2012 ImageNet challenge.
Yes.
And there was a sort of discontinuous effect.
Yes.
In some sense, that's the moment when time began for deep learning.
Yes.
Do you have any comments about what happened then or what has happened since?
Yeah, actually, I very clearly remember what happened that year. So in 2012, the entry we submitted to ImageNet was in collaboration with Xerox. And Florent Perronen, who was in Xerox, who was the winner of the previous editions of ImageNet. And so we started working on this entry in a rather confident way, right? We thought we're going to improve the previous approach, it should go well. And then I very clearly remember in autumn 2012, I visited Jan LeCun in Courant Institute. And Jan was more available, I think, at that time. So the usual scene when you would visit him, you would sit down in his office and he would share with you his latest advances and show you how these deep neural nets would work. But that year, he had sat on his sofa, and what he showed me is the NIPS paper, and that was the paper corresponding to the AlexNet, and the table with the numbers. And so, look, finally. Look at the margin, and I couldn't believe it. I was blown away. And then I came back in Grenoble, in France, and my team. I tried to share this with my fellow, and the atmosphere at first was very actually skeptical. So people would say, "Oh, but perhaps this is not significant. Because perhaps it's just an accident." And then. We arrived at NIPS, and Geoff Hinton gave this talk and showed these numbers with this big margin, and from that point on, things were never the same, right? So, I remember that year we would, register to NIPS. We could register late November, right? This year it was sold out early September, and few people cared about ImageNet back then. So that's something I would like to emphasize. So very few, if you look at the research team that would participate to ImageNet back then, actually very few. It was not that a consensual data set, even for computer vision. So the Pascal data set was, I think, more popular back then, and ImageNet really got a lot of attention after the deep learning results. And also the media exposure, obviously.
So is there some sense in which the competitions have undermined theory?
I think, definitely, although I'm not sure that's the cause. perhaps the media exposure of the deep learning results also did a lot of harm. But it's true that today, while the effort that is needed is building foundations of like understanding what deep learning is doing, trying to rebuild the foundations of machine learning and statistics, it's true that most of the effort is spent engineering methods that are already, that already prove themselves on benchmark data sets. And even like talking with students, it's not always easy to convince them to spend time working on a slow time scale, trying to build theoretical concepts to understand deep learning. Sometimes they're more attracted to just making incremental progress over deep learning architectures that were previously designed.
So one thing that's remarkable to me is that the competition as a method for improving the use of media is probably a 30-year-old methodology, and in every case where it's been used, it's been successful. However, over those 30 years, it was always different methodologies depending on the decade.
Yes.
So that there might have been some period where hidden Markov models were the great new thing, and there might be a period where support vector machines were the great new thing.
Yes.
But what was in common across all those experiences is that year in, year out, you would come back to a competition, say on fingerprints or iris recognition or facial recognition, and there would be steady progress. And the thing would start in the very beginning with very crude results and end with things approaching human performance. So in that sense, ImageNet is no different.
Yes.
And there is a case for saying it's simply the flavor of the decade.
Yes.
However, there are individuals who are very committed to deep learning, who believe they've reached the end of history. That
Yes.
there's no need for anything else.
Yes.
That a young person who's spending their time on anything else is misspending their life
Yes.
and wasting their main chance.
Yes.
Do you have any comments?
Yeah, I do have a comment. So there's one, I like to mention some computer vision results that were obtained in the 90s. So in the 90s, an important problem in computer vision was face detection. In 1996, there were two papers proposing neural networks to perform face detection. And then a few years later, methods based on cascade of detectors with some boosting were also proposed and achieved this, similar performance. So we had, and plus another method which was called SNOW. I think it's a kind of sparse coding method. We had three very different kinds of methods. By 2001, actually reached the state of the art for computer vision. Of the three, I think the Weiler-Jones detector, which is the boosted cascade detector, got most of the attention and is now available in all cameras. So the bounding box that is drawn around the faces. And then for several years, the computer vision community was passionate about boosting. And boosting was considered as the tool to attack vision problems. Strangely now, neural networks turned out to be the most effective methods for computer vision problem. And we still didn't understand why those three very different approaches at that time reached those results. So I think what's missing with all those benchmarks is actually looking backwards. So I think, there's a tendency to only be looking forward, trying to improve the results, but then as we accumulate all this empirical evidence, we should try to look back and see what happened, how come these very qualitatively different models achieved similar performance. So what does that mean? So like, is boosting essential to understand what a face is, or is a neural network essential to understand what a face is? And strangely, even for that problem, at least as far as I know, it was, so 2001, it was 16 years ago. As of today, I don't know any like scholar description of like, you know, what were those cascade capturing? How come they were performing as well as a neural network? It's still unclear. So I think there should be a long-term effort looking at the results of those competition at a different time scale, not the year time scale, let's say 10 years time scale, and try to understand what was going on and monitor the performance over the years and conduct sensitivity analysis, perturb the models and see what are the key components that made a difference. I think that's important. So in computer vision, this is done. It was done for the Pascal dataset. It was done somehow for the ImageNet dataset, but I think there's a significant effort to do now to understand what's going on, because I mean, if looking at the deep networks that were developed for ImageNet, it's just like now it's impossible to keep track. They're so huge, and also a concern is like now the winning entries for the ImageNet competition are mostly industrial labs, right? So academics can't catch up, at least with their computational resources. So this is also a concern, I would say.
Is there a theoretical idea that you would say could be very valuable in the current environment, but is not very well received?
So I think it's common to present kernel-based methods and neural networks as very different approaches. I think this is very misleading, and it's actually a very shallow point of view on these two methods. So kernel-based method is just a way to describe the Hilbertian structure once we've learned a feature representation, and the geometry of the data once we learn the feature representation. So I think so this has a very general value, right? And so I think it's commonly asserted in papers and that support vector machines are shallow architectures, whereas deep learning networks are deep. I'm not sure what. So I think this is started from a witty remark that was made in a paper by Benjo and Lokun. I think it was more made as to provoke thinking. It was not made to be like reused as a taxonomy of methods, but somehow like it's been cited again and again and reused, and but not always with great depth to talk about kernel-based methods. So I think reproducing kernel-Hilbert spaces, kernels, tools that are very effective to understand invariances, the geometry of the data once we've mapped it into the feature space, and also perhaps come up with more mathematically tractable versions of deep neural nets.
Thank you.
My first question is regarding unsupervised learning. I've noticed in recent times a lot of people keep mentioning unsupervised learning as the next possible big thing in deep learning. And from what I've seen, the main approaches are things similar to given a video and a certain frame in it, you try to predict, let's say, 10 frames ahead, or given a stack of cubes which are put one on top of the other, try to predict what happens when the cubes fall, like where will they be placed, or perhaps given a grayscale image, try to color it, etc. So these sort of things.
Yes.
I was wondering, what is your opinion about these methods, their chance of actually leading to unsupervised learning as people imagine unsupervised learning,
yes,
and the relation of these methods to your approach for unsupervised learning?
So I think, I mean, unsupervised learning, again, what unsupervised learning means is it's not supervised learning, right? So it's just a big jungle of approaches to do things that are not supervised learning. So there's predictive supervised learning, which has been advocated by Jan LeCun. There are also like traditional unsupervised learning approaches like K-means, PCA, and I think when applied with care to particular problems, they could lead to very interesting results, and perhaps give a way to analyze in a more clear way what training a deep neural net means, right? Rather than relying on stochastic backpropagation of gradients, which is.
Are you referring to K-means type of algorithms?
Yeah, I think K-means. K-means or like matrix factorization ways of training deep neural nets. I think those are like when we can derive statistical bounds for these methods, right? I mean, at least it's possible. So in principle. So I think those are promising. One thing that fuels the research in this area is machine learning researchers who are inspired by neuroscience, and so in their case they think that the brain is not doing backprop, and other learning mechanisms should be designed that are more biologically plausible. So I'm really unfamiliar with neuroscience, so I won't comment more on this, but I would say that's one of the motivation to come up with learning algorithms that are mimic what human beings are doing. I'm not sure it's a reasonable pursuit to come up with these algorithms, but still perhaps it's a way to try to go beyond backpropagation of gradients.
K-means sort of approach.
K-means or predictive supervised learning, or in computer vision there were also other approaches that were proposed where like they learn feature representation by using the neighborhood information of the image. I think there are many of them. It's not easy to keep track of them, but over the last few years, several of them were proposed, and adversarial training is also one of them. And this one got a lot of attention. There's a lot of research now in this area, and it's been considered by several leaders in the deep learning field as the most promising direction in this, as an alternative training algorithm for deep neural networks.
Okay. The second question from John Dushi is, could you propose a certain experiment that would either assess or maybe reject some of the claims that you're going to propose in the lecture? Validate them, basically.
Okay, so I think that's an interesting question. So one of the claims I'm making is that to achieve, at least on the data sets I've considered, to achieve a classification performance that is on par with the state of the art, it seems that data augmentation, which is the usual trick used by deep learning methods, may not be necessary if the appropriate invariances are built in the kernel that is designed. And so for this, the experiment is as follows. We train a deep net with data augmentation, and not the data augmentation, and we check if there is a significant difference. So we can only do this for small data sets. For larger data sets, there's an issue. I mean, deep neural nets are very computationally intensive methods. To train in a reasonable time, you need GPUs to run the experiments and to search over multiple parameters and multiple experimental setups. You need to launch them a multiple number of times, and this is and so for this you need clusters of GPUs, like hundreds of GPUs, and I don't have this as of today, but that would be an interesting experiment to run.
The last question is, metaphorically, if you were a layer in a neural network, which one would that be? If you could please specify the depth and the type.
So I would be any of the convolutional layer, because that's the only operation I fully understand.
And why?
Metaphor. Because it's just convolution is a well understood mathematical object. It's just clear, and so then I wouldn't care at which depth I would be.
Thank you.
Hi everybody, thanks for coming to this Gas 385 series of deep learning. Let's get started. So today we have Zaid Harchaoui from University of Washington visiting us. He actually was a participant of ImageNet competition in 2012. He got the second place after AlexNet. So he has a lot to tell you about practical deep learning too. Zaid has got a PhD from Paris Tech, and he was a research scientist at INRIA for 5 years before joining Quran Institute in New York and working with Yann LeCun. I think last year he joined the faculty of the University of Washington, and he's going to talk about views of deep nets from reproducing kernel Hilbert spaces. Without further ado, so listen to Zaid, please.
Okay, thank you very much. It's a pleasure to be here, especially to talk about this topic, that how to build a theory of deep learning, which I think doesn't get as much attention that it should. Before diving into the mathematical details, I'd like to go through the recent advances. You probably have seen similar pictures before, but I'd like to emphasize a few key components that I think are important. And also, I like vintage pictures, so it will be an opportunity to go through them. So, what is the machine learning ambition nowadays is to treat everything as learning dependencies between inputs and outputs from samples of pairs between the inputs and outputs. So you could take a text and then predict the topic of the text, or you could take a signal and then produce the speech transcription of the signal, or you could take an image and output a label corresponding to the main dominant object of the image. And the most successful approach to tackle all these approaches nowadays is a multi-layer neural network. So between the inputs and the outputs, or the examples and the labels, or the observations and the response, you insert a multi-layer network, which is this kind of architecture. So this is the graphical way to describe it. Mathematically, it's just a composition of particular kinds of functions. And so thanks to these kind of architectures and this framework, there's been very significant advances on several tasks. So this is what Dave Donahoe emphasized as a very effective mean to make progress on very specific problems, the common task framework. So in speech recognition, it's been a while that people have been using competitions to make progress. So TIMIS is just one of them. So since deep learning was introduced, there was a significant drop in the error rate for speech recognition. Another application that I'm more familiar with is computer vision. So back in the 70s, people used to work for image processing on one single image, the famous Lina picture. And then in the 90s, toy data sets where students would take objects and take many pictures of them, rotating the object and looking at different poses and different illuminations. So those data sets were very controlled. And at that time, the goal was just to recognize the same object under varying illumination, pose, rotation, translations, and so on. And then machine learning methods were introduced, and in the 2000s, people started working on real-world images and trying to do visual object recognition on real-world images. And for a while, those data sets, Caltech 101 and Pascal dataset, which is another very carefully collected data sets, were the dominant benchmarks for computer vision. And then ImageNet came in, and ImageNet, contrary to a common belief, was not such a popular data set when it was introduced. It was very popular among machine learning people because ImageNet is the perfect way to frame computer vision as a machine learning problem. It's computer vision made easy for machine learning folks. So you say computer vision is just multi-class classification problem, nothing else. So this was very appealing to machine learning people, but to computer vision people it was less appealing. And in particular, the way the data was collected through crowdsourcing without a strict control on how the images were collected, that was one issue with this data set. And one thing I'd like to mention is that in computer vision, one thing that made a big difference is how the labels were collected. So in the early days of vision, labels were given by researchers, so looking at the images and annotating them. In the early 2000s, people came up with a very clever way to have people, for free, give labels to images. And there was one very clever way, which was called the ESP game. So two people enter a game. They're randomly matched, and for a limited number of time, they have to label as many images as possible and agree on the labels. CAPTCHA was another way to label images that was very smart. And then Amazon came in and said, why have fun labeling images? Let's just pay people. And there was a major change in the way people started to collect the data sets. And ImageNet was definitely collected thanks to this technological breakthrough. But I just wanted to emphasize this. So it hasn't always been the case that we could label such large amounts of data. Okay, so ImageNet is this data set where you have real-world images labeled, and the images are centered around a particular object, and you have the corresponding labels. And again, in 2010 and 2012, the state of the art was basically taking SIFT features, which are local visual descriptors, which were considered at that time the best way to describe an image. But we'll see later in the talk that it's time to revisit this assertion. So they would take this and then collect a bunch of those local visual descriptors, and they'll build a bag of visual descriptors. And Fisher vector was a clever way to model distributions of local visual descriptors by a Gaussian mixture model and taking the gradient of the log likelihood of the Gaussian mixture model. That's why it's called Fisher. It's the Fisher score of the Gaussian mixture model. And then you add a support vector machine on top, and that was the state of the art before deep learning was introduced. And then AlexNet was introduced. And from that point on, the neural network kept growing in size and in depth. And ResNet, I lost track after ResNet. The performance was so mind-blowing that I stopped keeping track. So what are deep learning networks doing? They're combining in one single step, learning the feature representation that is mapping a complex observation. Complex not in a mathematical sense, but say like an image, which is a grid of RGB values, and vectorizing it, turning it into a vector. That's what we call feature representation. And the classification stage, which is usually the last stage, and it could be like a multinomial logistic classifier. It's usually equivalent to that. And so what deep networks are able to do, they're able to map images into those high-dimensional feature vectors. And the classification is usually linear prediction, or at least something that we understand well, such as multi-layer perceptrons. Those are nonlinear methods that we understand very well. Okay, and so how do they train this big chunk? They do stochastic backpropagation of gradients. So again, here I'd like to emphasize something. So it's a common assertion that backpropagation of gradients is just a chain rule. It's actually not exactly true. So I only know how to compose functions and compute the derivatives of composition of functions when they're differentiable. When they are not differentiable, I need convexity, and I cannot go further than 2 layers. So what does backprop do when it propagates subgradients in each of the intermediate layers? I have no clue. So perhaps it does something very meaningful, but I just don't know what it does. Probably it does something like local search, which is fine enough. But it's still widely used, and it seems to be effective. Okay, so that's the recipe. You frame the task as learning to map from input to labels. Then somehow you collect a huge training sample and you train using supervised learning and stochastic backprop. And then you're done. And this has been very effective. So recently I looked at the task of music transcription. So as surprising as it may seem, music transcription is still a very challenging problem. One of the fundamental tasks of music transcription is for any time in a music recording, determine the fundamental frequency of the note that is played. And for that, neural networks have been used, but they've never been trained on large labeled datasets. So I collected a dataset. The dataset is called MusicNet. It's the largest labeled music dataset. We trained neural nets, and guess what? When we compared on the published benchmark, which is called Mirex, we were the first this year. So this is breaking news. So as far as this experience is concerned, this recipe works. Now the issue is that this cannot be applied to any kind of problem, and especially when you look at scientific problems, it's unclear what this is doing and how you can implement this. So first of all, not all tasks can be framed as a prediction task. Okay, so even in computer vision, one striking example, say, assuming you want to do image retrieval. So say you have a bottle of Absolute Vodka. So this is actually, a company came to me asking me this question: how can we retrieve all occurrences of Absolute Vodka bottles in Instagram? Why? I don't know. So you're not going to take all pictures of Instagram and then start drawing bounding box or have people do it for Absolute Vodka bottle. I mean, it doesn't make any sense. Who would do that? Although perhaps some people would. But you're not going to do that for every single possible object in the world. Okay, so you can frame it as classification, but the bill might be very large. Okay, the other thing is, while it's very comforting to think of computer vision as a machine learning problem, it is not. Okay, so the purpose of computer vision, for instance, is to interpret the scene. So when you have this car in a pool, then what is wrong in this picture? What is this car doing in this picture? This is not classification, right? And collecting huge label training samples, this is extremely complicated when you look at scientific problems. So as soon as you need expertise in order to assign a label to a particular image, it's very complicated to just unleash that on Amazon Mechanical Turk and have people who you don't know, who have an expertise that is questionable, assign labels to the data you're giving them. Okay? So it's time-consuming, expensive, and often ambiguous. And finally, training deep conv nets results. So with backprop, which is an algorithm that's still a mystery, at least to me, results in non-convex optimization. And what is the landscape of the errors? How does local minima are related to the global minima? This is still unclear. There's some advances, small advances in these areas, but it is still unclear. So in this talk, I will question this methodology and try to propose alternatives. So this is what I call the wall of the current deep learning methodology. So this sequence of steps that is very effective every time you can indeed check each of those steps hits a wall. The other issue with that is I have no clue how to explain this theoretically. So those two parts make sense, but this part, what stochastic backprop is doing, why does it reach a good local minima, this is still very unclear to me. So I couldn't resist borrowing this picture from Yann LeCun that he presented at the Collège de France, where he gives his way of looking at the different parts of machine learning. And so he thinks that supervised learning is just a small part of all what machine learning is, and unsupervised learning is actually a large fraction of it. So of course, this is just a metaphor. We still have work to do. Okay, so multi-layer convolutional networks. So I'm going to present a family of convolutional neural nets that have a clear design principle that you can train with little or no supervision. and you can train also layer by layer, and each optimization problem that you solve at each layer is clear. And I've explored several applications. So with Julia Meral, we worked on image denoising and image retrieval. I've also applied it to motion estimation and music genre classification, but I mostly focus on the image applications. Okay, so let's talk about kernel-based methods. So I know this is very vintage, kernel-based methods. So nowadays, kernels look like this old method that no one is using anymore, but I like to resurrect them. So what is the idea of kernel-based methods? Assume that you have a training sample x1 to xn. Then instead of modeling it through some function that takes any input to a feature space, you're going to define a function that acts on pairs of examples, k of xi and xj. And you're going to assume that this function, which you interpret as a similarity measure, is a positive definite kernel. So this is great because it allows you to work on many data types. So you can define positive definite kernels on vectors, obviously, but also on strings, on trees, and in graphs. And the great thing with kernel-based methods is as soon as the function k is positive semi-definite, then you can interpret it as a dot product in some abstract space called the reproducing kernel Hilbert space. So what this means is that every time you apply this function, it's as if you were evaluating this dot product between those functions phi of x and phi of y in this reproducing kernel Hilbert space. It also means that since this is a Hilbert space, it means that your Euclidean geometry intuition holds in this Hilbert space. So you can use orthogonality, you can use dot products, and so on. So kernel-based methods are called smoothing splines in statistics. There's also a family of methods called generalized additive models that encompass kernel-based methods in statistics, and they've been very popular in the early 2000s, mostly thanks to support vector machines. Okay, so with kernels, you can actually model invariances. So for instance, if you take two real valued vectors, you can define, say, the Gaussian kernel, and this is shift invariant. You could also define kernels on sets. So say you take a set S1 to Sm, you can define a kernel on all possible pairs of elements in this set, transformed by the function S, and this gives you a kernel that is invariant to permutation. And then the great thing with kernels is when you combine them according to some algebraic rules, you can still get a positive definite kernel. So for instance, you can multiply those two kernels, and then you get a kernel that is both invariant to permutation and shift invariant, right? So you can control the amount of shift invariance thanks to this bandwidth of the Gaussian kernel here. Okay, so now the question is like, why didn't people use kernels for large-scale data sets? The reason is because kernel-based methods, as you write the solution of the optimization problem, involve either the inversion of the gray matrix, the matrix of all pairwise evaluations of the kernel, which is n by n, and therefore this scales in n cube. And so this is computationally expensive. And so what do we want? We want to find what we call an explicit embedding. So this is the term that is used in computer vision. That is a function psi that allows you to approximate the kernel as a dot product and is fast to evaluate. So one very popular example of those is the random Fourier feature explicit embedding. Okay, so now what happened in the 90s when neural networks were still popular? So keep in mind that between the rediscovery of backpropagation in 1985, 1986, and 1995, neural networks became very popular. There's also the creation of the Neural Information Processing Conference, which at first was a neural network conference. And then in 1995, there was a discovery. People thought, like, let's look at the neural net and with one hidden layer, and make the number of hidden units grow to infinity. What do these converge to? So it turns out that they actually converge to a kernel. So if you take for particular functions g, and for particular that acts on dot products between some omega and x and omega and y, you can write the equivalent kernel, so the limit of a neural network with an infinite number of hidden units, as a kernel that is positive semi-definite. So one example is if you take a neural network with exponential units, then you will converge to the Gaussian kernel. Okay? So then when people realized that, they thought, okay, so we could try this on experiments, and why don't we just do a kernel method with the kernel we find by analytical derivation, right? And in all data sets at that time, this obtained either results on par with neural networks or results that were slightly above. Okay, so another example is the Harchaoui kernel. So this is a very interesting one, because here you see what happens when you take hidden units that correspond to the ReLU. Okay, so this is another equivalent kernel to a neural network with an infinite number of hidden neurons. Okay, so this result was established in 1996 by Radford Neal and Chris Williams and Rasmussen. And as soon as it was introduced, it fueled research on kernel-based methods. So recall that support vector machines, the modern version, was established in 1995, right? And strangely, from that point on, neural networks started to decline. So this somehow contributed to the decline of neural networks, because people couldn't see why you would consider a neural network with one hidden layer with a finite number of hidden units, why you could consider one with an infinite number of them and have an analytical expression for the kernel. Okay, so I might be wrong, so of course this is questionable, this is just my personal view, but I think this contributed to the decline of neural networks in the machine learning community. Also, quite strikingly, this result was paralleled in other scientific communities. So in statistics and approximation theory, the works of Andrew Barron, and I learned yesterday that Emmanuel Candes also worked on this, in 1995. So people established, I would say, equivalent results to this, or equivalent mathematical observations to this. And also in system identification. So at that time, neural networks were used to control systems or identify systems. And in 1995, again, I mean, I didn't come up with these dates, it's really striking. So Bernard de Lyon, Anatoly Yuditsky, and Albert Benveniste also showed that if you use kernel-based methods, you could get system identification methods that perform as well as the neural networks that were used at that time. So another thing that contributed to the change is these results. So they were reported in 2002, but they summarize the progress on the MNIST dataset obtained by different methods. So I described what happened on the theoretical side. Now I'm going to describe what happened on the empirical side. So Jan LeCun and his collaborators has developed at the AT&T labs a sequence of neural networks, so LeNet 1, LeNet 2, LeNet 3, LeNet 4, LeNet 5, that consistently outperformed the other methods on the MNIST dataset. And then support vector machines came to maturity, which is one kind of kernel-based method. And by adding some data augmentation, so virtual SVM is a version of the support vector machine that incorporates data augmentation, so you jitter a little bit the examples. With support vector machines, we started to obtain results that were comparable to the neural nets. So I think the combination of these two events, the first, the realizing that infinite networks that had infinite width were equivalent to Gaussian process or kernel-based methods with particular kernels that in fact could be computed analytically. And on the other hand, the data set that got the most exposure in the machine learning community at that time, which was MNIST, the fact that kernel-based methods were competitive with neural networks, I think this convinced people that kernel-based methods were more promising methods than neural networks, at least at that time. Also at that time, I think, so I started my research in machine learning, I think my first research internship was in 2002, and I very clearly remember I tried to train a 3-layer neural network And at that time, even working on the cluster of the school, it was just impossible. So you would use stochastic Levenberg-Marquardt, and it was the nightmare. And then you had support vector machines, and you apply. So at that time, you could apply a QP algorithm or the SMO algorithm, which is coordinate descent, and it worked beautifully. You would converge to the optimum. You could reproduce the results in the paper. So it was clear for even for a fresh student, it was clear that kernel-based methods were much more friendly than neural networks. Okay, so then what happened? So in 2007, there was a symposium in the NIPS conference. And there's this paper written by Yoshua Benjo and Yann LeCun, where they made this point that there's two families of methods, the shallow methods and the deep methods. And support vector machines were considered shallow architectures. And I think this assertion made a lot of impact in the machine learning community. And it was probably misinterpreted. I think at first it was more of a witty remark or a provoking thought. But it was taken at face value by most people as, oh, SVM is just shallow, but neural networks are deep. Okay. But in fact, if you read very carefully what they say, so basically what they say is support vector machines with the Gaussian kernel, which is the most popular kernel used with support vector machine, that's a shallow architecture, and you can very well describe this. It's very close to nearest neighbor, basically, in a Euclidean sense. And this is true. I agree with this. But then, with kernels, you have all this wealth of kernels that were derived that are positive definite, that work on complex data, you can combine, and this statement doesn't hold for them. So I'm going to show now how to build kernels that are not shallow. So you take two images. I'm going to describe this for images. But you could apply this as well for signals, audio signals, or other kinds of data where you have a grid structure. So say you have two images, and you assume that the image is a grid, and you look at the pixel location z. And then you take another image, and you look at the pixel location z prime. This sub-image, I'm going to call a patch, and I'm going to define a similarity measure between those patches. But this is just the Gaussian kernel, and I multiply it by the intensity of the patches. So now I want to build some invariance to the pixel location. So I use the tool I described before. I just multiply this by a kernel on the pixel locations. So I have this kernel between the patches, and I have this kernel between the pixel locations. From this, I get a kernel between two images. So this is a very simple object. I have shift invariance thanks to this kernel here. I match the patches thanks to this kernel here. I'm not going to go into details on how you can motivate this, but you can motivate this from signal processing considerations. And then you have permutation invariance. Okay, so and then we have 2 degrees of flexibility. We can compare the patches by controlling the bandwidth of alpha, and we can also control the amount of shift invariance thanks to beta. Okay, and so this kernel is positive definite. It's trivial to show. And now what I want to do is to keep doing the same thing in a recursive way in a multi-layer fashion. So say I have an image here, and on top of this image I have a feature representation that stands on top of this pixel location that corresponds to phi m of z1, z1 being this location. I'm going to keep composing those kernels with each other in order to build further invariance. So I'm going to define what I call the feature map. So for any pixel location, I define a function phi k of m. So m is the image, k is the layer index, and z is the pixel location. And this carries information from the local neighborhood centered at the location z. Okay, so with this, I can go from a design of feature representation that is neuroscience inspired with the local invariance and aims to be as deep as possible, that's neural networks, to something that is concise and theoretically grounded. Now I can define the kernel at the next layer exactly in the same way. So I take this kernel acting on a feature representation standing in the location u and u prime, And then again, I sum over all pixel location, and I get another kernel. And I can keep doing that over and over. Now the question is, how do you compute this kernel, right? Because even at the first layer, it would mean that for any pairs of images, you will need to enumerate all possible patches and sum over all possible pixel locations. So for this, we need an approximation scheme. So this is where we use the explicit embeddings. So you can replace this kernel here by a dot product of high dimensional vectors, and then compute this sum, approximate this sum by the sum over all possible locations of this dot product. And then in fact, you can notice that this double sum, you can interpret it as a sum over all pixel location of a Gaussian blurred version of this image and a Gaussian blurred version of this image viewed through the representation MK and MK prime. Okay, so to build this, we need just a simple fact. So for the Gaussian kernel, so we can apply this for many families of kernel, but for the Gaussian kernel, it's very simple. The Gaussian kernel is the convolution of itself with a different bandwidth. So from this, you can get a factorization scheme. And so you can use, in order to approximate the features, to build this feature embedding, you can use either random Fourier features if you like Monte Carlo approximation. You can use Nystrom approximation or kernel herding, or you can use k-means, so you can cluster the z's, or matrix factorization, so anything. So all these methods are well understood, or you could do direct optimization. So in the results I'm going to present, we used spherical k-means as an initialization, and then direct optimization. Okay, so just to summarize, so what will we do? So for any patch located at location Z, we multiply it by a filter W. So we can interpret this as a convolution. And then I feed this through an exponential. And so I can interpret this as a nonlinearity that is not the ReLU nonlinearity, but instead an exponential nonlinearity. And then I have the pooling, which I can interpret as a Gaussian pooling. So here's the process. So you have the image. So, okay. At first, for any location, you have the patch. So you take the patch, you vectorize it, or you represent it as an empirical probability distribution. And as we iterate, you're going to keep subsampling the image and build higher and higher dimensional representations of the localized at each pixel location. And so this is a comparison between convolutional kernel networks and convolutional neural networks. So in convolutional kernel networks, what you do is you take pairs of patches in the two images and you learn a kernel similarity. And from this, then you leverage a new feature representation and you iterate this until you have completely subsampled the image. Whereas when you do neural network, what you do, you take the first image, you do convolutional nonlinearity pooling, etc., until you have those two feature representations. And then if you were to do dot product, you would do a dot product between those two. So this is the difference in the design. So in this sense, the convolutional kernel nets are not convolutional neural nets. They are completely different, but they use similar components that resemble the convolutional neural net. Okay, so this is a comparison of the nonlinearity. So this is the nonlinearity ReLU that everyone is using nowadays. And this is the nonlinearity that we are using, that we find when we apply the factorization of the Gaussian kernel in the convolution sense. So here I'm going to just go through the algorithm. So the way it works is you take the image, and then you extract random pairs of patches. You normalize the patch, and then you learn the explicit feature embedding by direct stochastic optimization, or you can do k-means, or you can do kernel herding, or you basically obtain similar results on all the data sets I'm going to present. And then when you go to the next layer, what you do, you normalize the feature representation located at the location Z. You feed it into a nonlinearity, and then you do Gaussian pooling. And then you can keep iterating this for each layer. So if you train a kernel convolutional net with several layers, you're going to train each layer one after the other.
So when you say in the training here, you don't look at the response yet?
Yes, never.
Yeah.
Yes, it's a completely, so it's unsupervised.
Yeah.
It's just looking at the marginal distribution of the patches.
Right.
Yes.
So you learn features by just looking at lots of things. but
Yes,
not-
exactly. Yes.
What's the loss in the training?
So all I'm doing here is just trying to reproduce. So let me go back. All I'm doing is trying to approximate the Gaussian feature, the Gaussian kernel, through this factorization.
Okay.
So it's as if I were, so you can, there are several ways to look at it. You could say I'm learning moments of the of this probability distribution, or you could say I'm trying to match this Gaussian kernel. But in the end, I'm never looking at the labels.
And so just random in that last slide, random WJs.
Completely random, yes.
Random WJs and PJs. We're
Yes.
getting pretty close.
Yes. Okay. So now so I can't avoid this slide. So it's the usual slide where we read the grounds of coffee, or we read the tea leaves. So we take natural image patches, hundreds of thousands of them, and then we look at the filters that are learned by convolutional kernel nets. And then, they look like Gabor filters. At least the first of them, first hundreds of them. How significant this is, I'm not sure, but at least the first of them look like Gabor filters, so we can say that the features that are learned by this convolutional kernel network resemble Gabor filters. So I had to do this because all deep learning papers do this. I don't think this is any significant. But let's move on. Okay, so now I consider image classification data sets, so MNIST, CIFAR, and SEL10. And here we apply to ourselves a particular challenge. We forbid ourselves to use dropout. We forbid ourselves to use data augmentation. And we forbid ourselves to use stochastic gradients. Okay? So what we do is we extract those random pairs of patches, and then we train the convolutional kernel network in a completely unsupervised way. Once we obtain this feature representation, then we train a support vector machine just the way we did in the 20th century. Okay? Okay, and here the challenge is like, can we do as well as neural networks that are very deep?
So the features at different scales, they're treated exactly the same? Or?
Oh, so I'm going to explain.
Sorry, can you repeat the question for maybe?
Yes, so Emmanuel is asking, how do I deal with the features that I extract at each layer?
Yeah.
Yes. So I do like any vision person would do, I concatenate them. I also report the performance for each of them. Okay, so this is with one layer, two layer, one layer, two layer. So I actually don't go that deep. I'm actually very shallow, and I'm proud of it. So, so I look at how the performance varies for different training size, and I compare the convolutional kernel nets with many neural networks that were proposed. So I mean, it's difficult to compare all of those, but basically the conclusion of this is that you get very close with this very simple procedure that is based on unsupervised learning to learn the feature representation and a simple support vector machine on those data sets. Okay? Yes?
So if you take an unsupervised learning and just literally replace it with the Monte Carlo Gaussian sampling approximation, how much
Yes.
do you
So in fact, random Fourier features don't work that well actually. Because you really need to, I mean, random Fourier features are blind to the data, right? So you do gain in doing Nystrom with data-driven centers, anchor points, or k-means. Okay, so you do get a drop. Now, if you, the direct optimization, so so you can try to do stochastic backprop to refine the performance. You just gain you get a few %. The other thing I should mention, so I tried, so while preparing this lecture, I actually did the data augmentation by looking at the transformations that were considered the most effective on those data sets on other deep learning papers. And in fact, and so the gain in performance you get is completely insignificant. Okay, so it seems that with this family of architectures, at least the transformations are not necessary because the invariance is built in, right? So you don't need to force this by training. Okay, so now I'm going to present other results. So this is an image retrieval application. So I don't have time to go into the details, but so image retrieval in computer vision is not understood the way we understand it in real life when we do Google image search. So to them, image retrieval is finding, so patch retrieval is finding particular key points in a particular scene. So say you have a scene and you have particular regions of the image that you want to match across scenes. Okay, so it's much more precise than matching images of different objects. Okay, so it's similar objects, but you want to find the exact correspondence between the patches. Yes?
I don't want to interrupt you too much, but Stéphane Malak also has a way of creating features.
Yes.
Not the same. And he also says that after I create the features, I can train, I can run either SVM or linear classification.
Yes.
Where would the performance of this method be compared to your approach? Do you know?
I think I'm not sure I have the.
Can you repeat the question?
Oh yeah. So Emmanuel is asking what performance do we get when compared to the scattering transform?
For example, yeah.
So that's the column SCAT1 and SCAT2
I see.
in the table.
That's a scattering transform.
Yes. Yes. Should I? Oh, okay. Okay, so image retrieval, so you extract the key points, then you build, you aggregate all those patches and you compress them into a big descriptor, and then you do nearest neighbor search in a huge database. Okay, so we compared on 3 data sets that are used for this particular problem in computer vision. They have varying size and varying properties. But basically the idea is that you have a particular scene. So one would be, say, the Oxford campus. You look at this particular building and you take pictures in different times of the day, different different locations, and then you want to match the key points of those two scenes. And you have different views. So Oxford, you have like 1,000 particular scenes and 5 views per scene, and UKB and holidays, those are also similar things. And the performance is measured in mean average precision. Okay, so the question here is that there's a common claim in computer vision is that the features that are learned by deep neural nets are universal. So let me define what it means. It means that you take ImageNet, you learn a deep network, then you have, for each layer, feature representations that correspond to different resolutions of your image. And then those feature representations you could use for any other task in computer vision. You can bootstrap them and then use them for, say, optical flow or tracking or this and that. Okay, so this is a common thing. And so when we did this, so it was 1 year or 2 years ago, the common belief was that AlexNet, if you take intermediate representations of AlexNet and you use this for image retrieval, a task for which it was not trained for, AlexNet was trained for image classification, then you should get state-of-the-art results. So actually the result is particularly striking. So it turns out that actually SIFT, this very old feature, outperformed the DeepNet, contrary to a common belief. So SIFT is a handcrafted feature representation that was designed 30 years ago. And compared to AlexNet. So the way we train AlexNet, so we look at AlexNet fully trained on ImageNet and we fine-tune it on a particular image retrieval dataset. And then we compare to unsupervised convolutional kernel nets, and with this we obtain results that are slightly above SIFT on those datasets. Since then, as usual, people designed a convolutional neural net that on those datasets does better than us, with more supervision. Okay, but that was expected. Okay, so it's not meant to be state of the art.
Is
this transfer of learning what you're showing us, which is like you train AlexNet for other tasks?
It's a kind of transfer learning, yes.
Okay, so,
yes.
so this
because
is also
and the reason is because for that particular task, when we first conducted this benchmark, it was unclear how to actually supervise an image retrieval convolutional neural net.
So these are just basically the features you learned from
Yes.
AlexNet on
Yes.
classification?
Yes, yes.
Okay, thank you.
Transferred here.
So there's another question.
Yes.
If you forced it, would it be possible to interpret your kernel network under standard CNN special setting? Like maybe, I don't know, like a special nonlinearity in conjunction with CME's network would lead to what you're proposing?
I'm not sure, so I didn't follow the last part.
The question is this a special case of CNNs under a very constrained, specific case?
So with specific activation, specific.
So you can. So if you want to match. So if you want to match. So you can. If you take an activation function that is a smooth ReLU, so smooth at the kink, and then you do the pooling, then it corresponds to one particular class of it corresponds to convolutional neural network with smooth ReLU and Gaussian pooling.
But
Yes.
in this case, you need two images, right?
What? No. So it's as if you were. So assume that you do the dot product between two images after they've been fed to a neural network and before the penultimate layer. So you look at the resulting feature representation over all these many layers. This you can interpret as a kernel. This is the statement. And you can also supervise convolution on kernel nets the same way you do for convolution on neural nets. So I refer, so there's a nice paper by Julien Méral who explored how you can train this just as you would train a convolutional neural net. But here, for the sake of making a point that there's a lot of potential in learning feature representations from unsupervised learning, I only focusing on the unsupervised learning part. Okay, so so it's an efficient method to design similarities between signals. You can train it in a completely unsupervised manner. It competes with convolutional neural nets trained with supervision on particular tasks. And in other tasks, you get a fraction of the performance you would get with neural nets with just an unsupervised learning procedure that is not stochastic backprop. Okay, so in this sense, I think it's a valuable way to learn feature representation that we can understand because it relies on kernels and you can input that to support vector machines or any kind of kernel-based method. Okay, so if you want to make it closer to convolutional neural network, then you can read this nice paper by Julien Méral on end-to-end learning with convolutional kernel network. So he does the backprop for this and so on. And he obtains slightly better results than the ones I reported. Okay, so now I'll finish the talk with a future research direction. So the first thing, so since all the things I've described are based on kernels, so I could apply this to videos, music, text, any kind of data that is for which I can define kernel that is positive definite. The next question is, now that I can define analytically the invariance that those kernels enforce, is how does this interact with the marginal distribution of the observations, right? So once I train with this unsupervised learning, how does the smoothness of the reproducing kernel Hilbert space, the invariances enforced by the kernels, and the sample interact with each other? And this would be useful because then we could learn from never-ending streams of data. Okay, so I finish on this. So it's just a message on theory. So while preparing this lecture, I was wondering, so why do we need theory? Okay, so it's a question I always get from students. Why? Who cares? Or there's also someone in industry who once asked me, how is this useful to us? So there are several reasons. The first one is there's the delight of analyzing mathematical objects. So I understand it might not be appealing to everyone. But I think it's fair enough with motivation, right? The other reason is that if you want to know how a particular method behaves in particular strange, unforeseen situations, there are two ways to proceed. One is actually to have this situation happen and experiment with it. The other way is actually have a theorem that says, in this setting, this is how it's going to behave, right? So if you want to know how disasters can happen with machine learning systems, there are two ways to do this. One is to have the disaster happen and actually observe how the disaster goes. The other way is actually to have a theorem that tells you what's going to happen and how robust your machine learning system is. So I'll quote here Norbert Wiener, who is who created cybernetics, which is one of the root field of machine learning. And he makes this point that that is visionary. So recall this was in the 50s. And when asked about safety of cybernetic system, he says, again and again I have heard the statement that learning machines cannot subject us to any dangers because we can turn them off when we feel like it. But can we? To turn a machine effectively, we must be in a possession of information as to whether the danger point has come. The very speed of operation of modern digital machines, so that's in the 50s, right? And there's no GPUs. It was already clear to him. Stands in the way of our ability to perceive and think through the indications of the danger. Okay? So now the question is like, are those disasters real? So there's been lots of blogging and this armchair debating about the safety of AI systems, but my claim is actually disasters are already happening. So you're all familiar with TIE, which is this dialoguing agent launched by Microsoft Research, which started dialoguing and was learning from data that was input by the individuals it was interacting with, and very quickly started making racist and horrible statements, right? And then what did they do? They turned it off. Okay, so you wish in this case that the disaster didn't happen, right? So you wish that you could foresee the disaster, perhaps thanks to mathematical tools. So I think this is a very important motivation to study, to build a theory of, and this is not specific to deep learning, it's specific to any machine learning method. It just turns out that linear methods, we know very well how robust they are. Methods such as deep learning, we don't know yet. It doesn't mean they're bad, it's just we don't know, we have no clue. So the question is like, how can we certify the robustness of a machine learning-based AI system? So I'd like to mention here the great works of John Ducci's group and Percy Liang's group, both at Stanford. But there are actually very few researchers looking at those problems nowadays. Because how can we safely unleash machine learning-based AI systems in the wild? So that's a question no one asks in industry, but actually, so they just unleash them and see what happens. But we're going to see a sequence of disasters and very unforeseen events with machine learning systems, and we wish we could foresee those behaviors thanks to mathematical tools to certify to extents to which a machine learning system can be robust to the data it was learning from. So we need more theory, and we need you. So I'll finish by thanking my great PhD students, so Corinne Jones at University of Washington, Mathis Paulin, and my amazing collaborators, Cordelia Schmidt, Florent Perronin, Matthijs Douze, and Julien Méral.
Thank you, Zaid. So we're going to start the Q&A session, and at the end you'll get some audience participation. But before we get there, I'm going to ask the questions that students posed. One of the common questions that student had was about the computational complexity of kernel methods compared to basically CNNs and so on, and
yes.
Also memory requirements of these methods, and they're asking whether it poses challenges for these methods.
So in fact, now there are great software tools that were proposed for deep learning systems that we can use to implement convolutional kernel-based methods. So we have an implementation. So we have an implementation that is online on MATLAB that doesn't leverage GPUs. And there will be implementations in Python that use GPUs, and you can implement this in PyTorch, for instance, or TensorFlow. And the results I presented in CIFAR, it takes roughly 20 minutes to run them on a machine with one GPU, a Titan X.
Okay.
So it's reasonable.
So, and maybe a relevant question that some students ask, would these methods also be able to do transfer learning? So can you do transfer learning on the kernel methods like you would do in AlexNet, for example?
Oh yeah, yeah, sure. I think so.
Awesome.
Yes.
Okay.
And you can analyze it.
So is Yvonne here? Yvonne Roseman? Okay. So maybe you'll ask your own question because I thought that's an interesting question. So.
So I looked at the kernel-based methods for hypothesis testing paper.
Yes.
My question was, regarding calibration of the test statistic, how if you're using bootstrap methods, you could be able to preserve the covariance structure in like what might be sequence data, but still get an accurate measure of how to calibrate your test statistic. Yeah, I think that's basically my question. Does that make sense?
Yeah, sure. So the question is like, does bootstrap work for kernel-based methods?
Particularly if you're using like sequence-based data.
But what do you mean by sequence-based data?
So like the example in the paper was...
Oh, dependent data?
Yeah.
Oh, so yeah, I think that's a very interesting question, whether Bootstrap gives... So for this particular family of statistics, whether Bootstrap gives accurate significance, critical thresholds when you have dependent data, I don't know. I think it's an interesting question. I mean, definitely dependence breaks the accuracy of the Bootstrap in this case. So you could do block Bootstrap, although I don't have any precise result stating that. But it's plausible that it's the case.
So Nima has a question. In the paper's conclusion, the author brings up the idea that the use of supervision might help to better approximate the kernel for the prediction task. Considering the observation that the first layer of the convolutional neural networks are usually similar, even for different tasks, is it better to add supervision to the first phase or use more unlabeled data to improve the quality of the kernels? So you want to elaborate on?
So let me rephrase the question. So the question is like, where do we inject supervision to learn?
In phase one, you're saying that it's better to, it's a good idea to, it's a good idea to add supervision to phase one, that you're training kernels.
Yes.
This is a future, direction that you mentioned in your.
Yes.
And I'm saying that the fact that many people observe that, as you were saying, that in AlexNet the features are kind of universal. Is it better to add supervision to that phase, or to add more unlabeled data?
Yes.
To improve your training.
No, I understand. So I think if you care about performance, surely like going the supervised path is the way to go, right? So I think the question is like, even if you do supervised learning with convolutional kernel networks, the resulting optimization problem that you're solving, it's difficult to. It seems very challenging to derive statistical guarantees on the solution you may find. Whereas if you do layer-wise training with unsupervised learning, it seems more tractable. So here the question is more. So I think the main focus of the talk is like, are there ways to train neural nets or kernel nets that are amenable to statistical analysis or theoretical analysis compared to the most common way, which is like supervised training with stochastic backpropagation, which leads to good performance, but it seems like out of reach of theoretical analysis as of today.
I've one specific question which I think some people will be wondering about. Okay, so the deep net paradigm exists, and you have to live with that reality.
Yes.
So you're proposing a different way to construct predictions based somehow motivated by an unsupervised point of view.
Yes.
But and you mentioned that this can be done somehow within a PyTorch framework, but just for the benefit of people who can't see their way to that.
Yes.
Do you imagine that you can one day see this implemented in a way that the choice of whether you use a conventional deep net or you
Yes.
use the kernel nets that you're offering is just basically the typing in some words in a parameter choice file, and everything else seems to work just the same? Or is there going to be some difference in the way you organize your life because of the choice between deep nets and kernel nets?
Yeah, so I think especially PyTorch has such great abstractions in terms of how you. So in PyTorch you can define general pooling operations, general convolutional operations, and then you can define your network by just composition of these, and then it just takes care of sending this to the GPU or CPUs, right? So you can by leveraging those abstractions, the programming abstractions, I mean. You can implement this in just as efficiently as a convolutional neural net, and that's owing to the amazing work they did for PyTorch, right? You could do that as well with TensorFlow, but I'm not, I didn't spend enough time with TensorFlow to tell you how you could do this in detail. But for PyTorch, I know. Yes, and you can do this with Café as well. So yeah, so it is possible that this can be equally trainable in comparable time than a standard convolutional neural net trained in a supervised way.
So it had occurred to me anyway, and you please correct me, but since you're using something that is somehow axiomatic and derived, it somehow has fewer parameters.
Yes.
So it had occurred to me that somehow you need less data to train the system, and somehow the prediction that you produce is intrinsically less noisy for the same amount of data. But I didn't really see it.
No, it is true, and that's what I call conciseness. So with those kernels, you can compete with neural nets that are, say, 12 layers deep with just 2 layers. So it's more expressive. So because you use this kernel framework, you can get a more expressive modeling of the invariances, and therefore you can afford to stack only a handful of layers instead of like very deep layers.
Okay, one more, and then we'll go back to the student. At the beginning of your talk, you had spoken, you had quoted from, I imagine it was Bengio and LeCun,
yes,
about how kernel methods were basically just nearest neighbor methods.
Yes.
And then you've proposed a new kernel method.
Yes.
So what's your distinction between that and the original critique of how have you changed the game to evade the critique of Bengio and LeCun?
So I think their statement only holds for trivial kernels, such as the Gaussian kernel directly applied to the pixel values of the image, in the case of image classification. And as soon as you consider structured kernels or more complicated kernels, I don't think their statement holds. And in fact, if we look very carefully at what they say, they seem to imply that. So I think, they say, it is possible to use kernels that are non-local, net data specific, Most practitioners have been preferring linear kernels or local kernels. So their statement is more restricted to like very popular kernels applying in a completely straightforward way to the data. And the kernels I've built are composition of kernels that are more structured kernels. And in this way, I think they can be considered deep kernels in their terminology.
open the audience, the question to audience, and so John Ducey had a question. Just
So when I think of, so you defined a new kernel, which evidently represents some Hilbert space. And so when I think of Hilbert spaces, I like to think of sort of examples that have small norm in them. Do these compositional kernels, is there any intuition as to what space of functions they represent
yes.
well?
So you can describe the RHS norm, the RHS norm of those kernels in specific cases, and you can use this to regularize those networks. Yes.
Do you have any way of explaining to us what that space looks like?
So it's in fact not so easy to, like in a few words, to summarize this. But what we find out is actually very related to the scattering transform. So it's very related to semi-discrete frames and theory, and like standard objects in frame theory. So. So I have a paper coming up, but you can also look at, Alberto Bietti and Julien Meral have a paper where they consider this, so that's...
So anybody else has a question?
I was wondering if the point of view of convolutional kernels can shed some light on some common tricks in deep learning. That's one question.
Yes.
And the second question is from one of the people in the Q&A. He asked, is this likely to be better when facing adversarial attacks? Like if you try to fool a network by adding some evil noise.
Yes. Okay, can you remind me your first question?
Can you explain some tricks using this?
Oh yeah. I mean, there's numerous tricks in deep learning, so it's difficult to.
Pick one.
Yeah, sure. So one of them is data augmentation. Data augmentation, that is like taking images and jittering them and transforming them, and then including them in the training data. That's a trick that is useful when your built-in feature representation is not invariant to those transformations that you're trying to simulate, right? So if the kernel is indeed invariant, why would you need to feed data that emulates this invariance? It's just redundant. Okay, so those tricks are useful. So for instance, if I want to do JPEG compression artifacts, so this is a transformation that is not modeled by this kernel. So that would be useful for this kernel, for instance. But then translation invariance, rotation invariance, not clear whether it would be useful in this case. Another trick is dropout. So I think dropout, I mean, there were very clear papers. I think Percy Liang's group had a paper about this. David McAllister had a paper about this, showing how dropout actually relates to L2 regularization. Yes. So I think that there were very clear papers addressing this. So dropout is a way to computationally emulate L2 regularization when you do stochastic training. So viewed as this, it is useful here.
So what about the adversarial things?
So the adversarial thing, so let me comment on this. So this one is very important. So I think, there's a common belief that deep nets can do just anything. Okay, so there's been this series of papers, I think last year and this year as well, where they say, okay, so a deep net can learn anything. So if I wanted to be robust to adversarial example, I'm just going to create adversarial example, and since it can learn anything, it's going to learn those as well. Okay, so this is a trick. It may work, it may not work. How robust is your resulting network once you've done that? You still have no idea when you do this, right? Because this is completely experimentally driven, right? So actually, John Ducey has a great paper. Is it online?
Which one?
The distributionally robust. Yeah. So there's a way to approach this from a very principled point of view. Read John Ducci's paper.
So I also have a question. So a mystery in deep learning is that these methods have a lot of parameters and the data is not enough, but still they generalize very well when it goes to test data. So you seem to have a theoretical foundation, and based on that, you're building this thing. Is it possible that you study the generalizability of these kernel networks that you're
so the work I presented is work in progress. So there are some things I have done, I have published, and there's also work in progress. So the statistical analysis of those kernel convolutional networks, this is a work in progress. But now, since we are manipulating kernels, we know the norm, the reproducing kernel hyperspace norm. This can be done now. So it's more clear for this family of methods than for convolution, regular convolutional neural networks.
Okay, let's thank our speaker again.